Today we're talking about absolute maximums and minimums, or maxima and minima, as your book likes to call them. And I have the definition of an absolute maximum here, and it looks terrible and difficult to understand. It's really not. I'll draw you a picture in just a second. This says that a function has an absolute maximum at x equals c if f of c is bigger than or equal to f of x for all x in the domain of f. So let me draw a made-up function here for you, and we'll just notate where its absolute maximum is. All right, so here's my function f of x, and the absolute maximum of this function is going to be pretty easy to spot. It's going to be this spot right there. That's going to be the absolute maximum. And that is because its x coordinate is the x equals c the definition is talking about. So here's the c, and it says it's the absolute maximum because f of c, that's the y coordinate at c, f of c is bigger than or equal to f of x for all other x values. This means that c's y coordinate is bigger than all of the other y coordinates for the rest of the function. So it's kind of a peak, but it has to be the biggest peak for the whole function. We have another peak over here. This one later in the chapter, we're going to call a local maximum. But in this section, we just want to focus in on the absolute maximum and the absolute minimum. We want to think about this too. So the only difference in this definition than the one on the previous slide is instead of maximum, I say minimum, and I flopped that inequality around the other direction. So this is going to be the lowest y coordinate on the entire function. So I could draw some kind of crazy function, and then the lowest y coordinate would be our absolute minimum, because it's the lowest y coordinate that this function ever achieves. And again, we'll identify local minimums. This one has a couple of them a little bit later in chapter 4. So I posted a ton of graphs under the resources for the week for us for this section, and we're just going to go through them one by one and visually identify where the absolute maximum and absolute minimum of these functions are. So this is our first function here, and it's got lots of little places where it peaks out, and this one is the one that we're going to call the absolute maximum. So this is the absolute max. So the absolute max is the y coordinate. So we're going to say the absolute max is 6 at x equals 10. So we'll say what the maximum or minimum value is and then say where it happens on the x-axis. All right, so our absolute min is going to be down here at this little cusp. That's the lowest y coordinate I see. So this is going to be our absolute min. And that is 1 at x equals 8. Next graph looks like it's the graph of y equals x cubed. This is an example of a graph that has no absolute max and no absolute min. So this is a possibility that you don't have one of the two or both. And this is because this graph, because they've drawn it going to the edge of the graph paper, it implies that it keeps going in that direction and it keeps going down towards negative infinity on the left. So this means you're never going to arrive at a y coordinate where there's not another higher one after that, because this thing keeps going towards infinity. And same thing as it goes towards negative infinity. So we're going to say that this function has no absolute max or min. All right, here we have one of our trig graphs. This one looks like it might be cosine. And when we look for the biggest y coordinate around, it happens over and over and over again. And the question is, does that still count as an absolute maximum? And the answer is yes, it does, because in the definition, it said that the y coordinate of the absolute max had to be greater than or equal to every other y value in the function. So this function has its absolute max repeatedly. We're going to assume this is the cosine function, so we know it's going to go on forever and ever and ever and continue to hit that y coordinate of 1. So we're going to say that the absolute max is 1. And that's at x equals, let's see, it happens at 0. And then it happens at every even multiple of pi. So we'll say plus or minus 2 pi, plus or minus 4 pi, we're going to assume. And then we'll kind of say, you get the idea. It keeps having this repeatedly. Likewise, the absolute min happens repeatedly. These are negative 1. All right, so our absolute min is negative 1 at x equals all the odd multiples of pi. So we'll say plus or minus pi, plus or minus 3 pi, comma, dot, dot, dot. You get the idea. This is happening over and over again. All right, another piecewise function that appears to be a lopped off version of some other graph. And we've got our absolute maximum, again, happening at one of these filled in endpoints. So this is my absolute max, is the y-coordinate is 4 at x equals 3. And this one also has an absolute min, not at the other endpoint, but in between, kind of at the vertex of this parabola looking thing. So we're going to say the absolute min is 0 at x equals 2. Next graph, this one also appears like the x cubed graph to not have a maximum value. So we're going to say there's no absolute max. We got this graph going off towards a vertical asymptote. We know those go on forever without stopping. But we do have this filled in circle down there at the origin. So this can count as the absolute min. Okay, so the absolute min is 0 at x equals 0. This is our last graph that we're going to investigate visually. We have the absolute max here on the y-axis. So our absolute max, this is the biggest y-coordinate, is 1 at x equals 0. But then the ends of this graph on the left and the right kind of imply that we've got a horizontal asymptote at the x-axis. That's the best guess we can make from what we've been given on the graph. So this thing is going to keep getting closer and closer and closer to the x-axis forever in both directions, never actually touching, but always getting lower. So because it's always getting lower, there's never going to be a y-coordinate that we achieve that the graph never goes below. The graph never goes below y equals 0, but because it's a horizontal asymptote, it's not ever actually equal to 0. So we can't use it as an absolute minimum. So we're going to say we have no absolute minimum. So maybe you didn't notice as we were going through all those graphs, but all of our absolute maximums and minimums, or our absolute extrema, happened at one of 3 different kinds of places. We were either at an endpoint, one of those big filled in dots, or where f prime of x is equal to 0, where we have a horizontal tangent, or where f prime of x is undefined. So endpoints, that was like this one, we had our absolute max up here at that endpoint of the interval. We had a couple of them that happened where f prime of x was equal to 0. Our absolute max on that last one was here on the y-axis, where we would have had that horizontal tangent line where the derivative would be equal to 0. And then way back on the first graph, we had our absolute minimum here at this cusp. That would be a case where f prime of x was undefined. So when we're looking at the formulas of these functions, we want to be able to identify where these absolute maximums and minimums might be. We're going to be looking at any place that's an endpoint of an interval where the derivative is equal to 0 or where the derivative is undefined. Those last 2 bullets where f prime of x is 0 and where f prime is undefined, we're going to focus on those in the next video. We're going to call these kinds of points critical points. And critical points are going to be very important to us going forward for the rest of chapter 4.